Good afternoon. I'm Parag and I'm going to present a structured approach to predicting image enhancement parameters. In past some years, there has been pretty active interest in the field of machine learning based enhancement methods. So this is a outline of basic machine learning based method. So you have a original image, then you do some kind of feature extraction and you learn a model to quantify the visual appeal, and then uh, that's your basically training stage. Now when you have a new image, for sure you have a model to choose the highest ranked beautiful image, but where to get the images to choose them from? So you do feature extraction, and then you uh, you find the nearest low quality training image, and you do parameter sampling to create hundreds of candidate images, and from them you choose the best enhancement for a new testing image. Now such approaches are very attractive. They may learn from massive amounts of web data. They can make personalized enhancement systems, and high quality enhancement may be possible on low cost devices if the approach is a purely model based one. But what is preventing all this? It is we believe it is this stage. So for a new image, you need to connect with the training data set, which might be millions and millions of images, and then you need to do parameter sampling to create candidate images, which are in the order of 200 to 300 candidate images. And then you then you do feature extraction for all those 200 images, and then apply your learned model. So the cons are frequent access of training data is required, then high search costs associated with the KNN technique, and the enhancement parameters set may well be suboptimal since it always lies near a subset of training image parameters. Now, how do we enhance an image? Given a new image, we don't really go back to refer some training images. We have a fair idea that okay, this image looks dark to me, so let's enhance it in a particular range. So we might, there is a slider or some interactive software, and then we choose the image which we like the best. In this case, I like the middle one better. So we our approach is to model this determine this enhancement parameter based only on the test image. So we model this as a matrix factorization problem. So we hypothesize that the parameter value um, can be expressed as product of three latent matrices. The first latent matrix models the relation across images, second latent matrix models the relation across the enhanced versions, and third models across parameters. Now, such a dataset is difficult to get, though it's uh, made available by MIT out of 5K, which has 5,000 original images and 5 enhanced versions for each image. So we do training, validation testing with 4,500 and 500 images respectively. Now for quantitative analysis, we just compute the root mean square error between the ground truth parameters, which are calculated from the enhanced versions of MIT dataset, and the ones which we predict. So uh, the details are on the poster. Our approach gets the best RMSE, and we also did subjective tests for obvious reasons with 11 people and 35 input images each. They were told to select the best image from our approach, Picasa, and the approach of this is a CVPR paper which is learning to rank for image enhancement. So we can see that KNN sometimes produces overly saturated or undersaturated image, and more importantly, it needs to just constantly interact with the training set. Whereas our proposed approach is just takes the image, calculates its features, and then uh, you can get parameters from this. The details I can say more about in the poster. So it KNN actually does sometimes well, but the point is not beating KNN. The point is doing it without a training set so that it can be implementable on low cost devices. So basically, we introduced a matrix factorization inspired approach to the novel problem of predicting image enhancement parameters, and results show that we can predict them within a reasonable range without referring to the training set at all, hence saving a lot of computation. It's just at test time we just need to take inner product of three matrices, and this type of approaches can be used to deploy standalone machine learned enhancement systems on low power devices. Thank you.